Professor Hu, please.
Hello everyone. I hope the sound does it work? You can hear me? Anybody can hear me? Hi.
Yes, you're okay.
Oh, thanks. This is Sheng Hu from Shang University. It's my pleasure to join this conference, actually join this community. I have learned quite a lot from these fantastic talks, but my topic today is slightly different than the others. It's about hydrogen isotope separation, but I still can hope to have some helpful discussions later. So, we know this deuterium and tritium is actually the fuel of these fusion reactions and be useful for many other things. However, their production is still a very difficult task because on one hand, it's very expensive and both capital and energy. On the other hand, it requires extremely high temperature and harmful chemicals, and thus it needs a lot of separation stages. So efficient hydrogen isotope separation technique is critical in nuclear energy related areas. So our solution is to use 2D materials. Using 2D materials for separation is not something new because of its atomic scale thickness that can maximize the flux. However, if you see, this is the lattice of graphene. It looks like there is a pole in the center of the lattice, but actually it's covered by electrons. So what can permeate through these two-dimensional lattice? Well, electrons can go through either through tunneling or just through, graphene is a conductor, obviously can go through. On the other hand, there is nothing can go through this one atom thick lattice. Even for the smallest hydrogen, it takes something like 1 billion years to, if ever have a chance to tunneling through. So you see, the electrons can go through, but atoms cannot. So what about subatomic particles? That is to say, protons. Can they go through defect-free 2D crystals? So we tried to design some proton conductive circuit where only protons can go through, but no electrons can go through. So we measured some conductivity. It's unexpectedly protons can go through two-dimensional materials and with unexpectedly high proton conductivity even at room temperature. The mechanism behind is, at least we think, is related to the electron density in the lattice. For graphene, it's a conductor, so there is a lot of electrons in the lattice and block the proton transport. However, for boron nitride, it's an insulator, and the electrons are more localized near the nitrogen atoms, so it's more porous compared to graphene, and it has a higher conductivity. So the proton transport through 2D material follows this Arrhenius type of behavior, which means it's not tunneling, but thermal activation. And obviously you can use some like catalytic method like Latin nanoparticles for catalyst and some light effect to even enhance the proton conductivity. So it's a very efficient proton transport membrane. Okay, so this is some kind of our background of what's happening. So now, if you put deuterium in this system, I mean, replace all the proton source with deuterium, you will see that the deuteron transport is 10 times slower than the proton. And this 10 times difference is independently of the 2D crystals used. So you can translate this 10 times difference into the energy difference, the transport barrier difference between these two particles, which according to this Arrhenius type of equation, you got 6 MeV. So I want to say this is actually the proton sieving in the you can design certain kind of device, and you can prove that all the electrons have in this circuit have been used to reduce the protons into hydrogen. That is to say, it's 100% efficient electrochemical pump. And you can thus use this pump to separate actually hydrogen isotopes. If you put mixture of hydrogen isotopes on one side of the circuit and you apply a potential, you drive these protons to go through the membrane, and then you reduce it back to the gases on the output side. You can achieve actually very highly efficient H over D separation. For example, is you can put this conductivity data with this real device separation data. You put them together, you found they are actually talking about the same thing, which is the activation energy of the two isotopes are different by 60 MeV. So where this comes from, you know, our proton is not injecting from the vacuum, but actually through this hydrogen bond, where the OH and OD are bonded through this, H and D are bonded with these oxygen atoms. So that's their initial state. When they transport this zero endpoint energy, not only lifts their energy levels, compare that with vacuum, but also there is 60 MeV difference between H and D. That's why they have this certain kind of separation factor over 10. So it's some cartoon that shows what's happening. So when this 0 point energy can help these light protons to go through the wall, which is the transport barrier from the electrons to the lattice. However, when a heavier deuterium comes, it may not as lucky as the protons. So it's quite remarkable. It's at room temperature and using very easy electrochemical pump, and you can achieve 10 separation factor over H and D. But can we use it? You see there is some, it's highly demanded actually. But if you really want to use it, at least these membranes have to be scalable. So to prove that, we developed a hot press method using CVD graphene. At least we can make it in centimeter scale, and we investigated their separation factor and energy cost. So this is kind of a summary of all the existing hydrogen isotope separation method. You can see they either have very low separation factor or have relatively high energy consumption. So if you put 2D materials data here, you can see they increase the separation factor by almost like up to 99% of the energy. So if following our mechanism, actually we predicted that tritium separation into the materials would be as high as 30, but it needs to be experimentally investigated. So this part summary is protons can easily pass through atomically into the crystals, and there is novel phenomenon, large isotope separation factor. So that's about this proton transport through this vertical direction. During our research, we actually were thinking of something different. You know these Van der Waals crystals, which like graphite, they are layered structures. There is some Van der Waals gap between the layers. If you calculate, you will find this gap is very close see if there is anything new and if there is any hydrogen isotope effect because of this quantum effect. So we designed some devices which have interlayer channels for the protons to go through. And indeed they can, but only for certain materials. So the hydrogen hexagonal bond nitride, the interlayers have the highest proton conductivity. We think, again, it's related to the electron cloud density in the interlayer spacing, because the hexagonal bond nitride is an insulator. However, when you look at the data more clearly, you will find there's two kinds of contributions for the protons to go through the interlayer space. So one is the entrance resistance, which means when the protons enter the channel, it has a barrier, and it also have a barrier when it diffuses inside the channels. So the diffusion inside the channels is quite normal, which follows classical theory. The resistance is proportional to 1/√m. However, if you look at the entrance effect, something different is happening. You will find that the heavier deuterons can transport even faster than the lighter protons. So this is so-called quantum sieving effect, but previously it was only being observed in low temperature. In our case, we think this is because the interlayer spacing, the size is actually comparable to the matter wavelength of this, proportional to 1/T. So at room temperature, it's only 1 angstrom. However, according to our data, we can calculate that the effective size of the protons field about this interlayer channel is only about 0.5 angstrom. So what's happening here is because the heavier deuterons have a higher, larger mass, which means the wavelength is larger, and that means it has larger size in the quantum world. That's why it transports. The hydrogen has have a lower mass, and thus it has a longer wavelength. That's why it transports slightly slower than the deuterons. So according to this research, actually we were thinking about how to actually achieve room temperature hydrogen isotope separation. Our idea is through atomic scale pores and channels. So you see, we need angstrom scale sized pores and channels to achieve this hydrogen isotope separation. So this size is actually comparable with the lattice parameters of any crystals. So, well, there is a lot of ways to construct these pores and channels, but our idea is to say, okay, why not we just use these lattice pores and the lattice, like these two-dimensional channels of the lattice to achieve that. So recently in Xiamen University, we are doing things like that. We can try to synthesize some materials that match our demands to achieve the room temperature hydrogen isotope separation. For example, we can design some polymer membranes. It's like graphene, it has a lattice pore. The size of the pore can be controlled by these monomers which were used to synthesize such kind of polymers. Also, we can even use chemical groups substitution technique to even control the subtle atomic scale details on the interior of these pores. So using these materials, we can actually achieve the quantum sieving at room temperature. That is to say, we can actually separate different hydrogen isotopes. So, so one sentence summary, at least I think, is there is various 2D materials to be designed and discovered and to achieve hydrogen isotope separation, which could facilitate the research, for example, the fusion research, as this conference many people talked about. At least we can facilitate the development on this area. So that's the end of my topic. I would like to thank all my colleagues and collaborators, and thank you for your attention.
Yeah, now is a question and answer time.
Can I ask a question about this industrialization? Because the separation of deuterium from hydrogen is quite important. So for your method, can you see the economic situation that the 2D materials can be utilized for the real separation of heavy water?
Yes, thanks, Professor Qian, for your question. So at least according to data from the prototype devices, it looks quite promising, because the important thing is it can work at room temperature, and you see we can use a very easy electrochemical pump to separate H and D, which is compared to the current method, which requires extreme high temperature and some harmful chemicals, and also it costs a lot of capitals, and the plant size is actually very huge because it has hundreds of separation steps. And in comparison, you can actually use, we actually done the estimation, you can use 30 square meter 2D materials to replicate the production of heavy water of a whole deuterium separation plant. That's quite impressive. However, at this moment, we still need to develop high quality 2D materials and how to make a large scale devices. I think that's the bottleneck for the next development.
Thank you.
Thanks.
Any question? I have no question. I have a comment. I think this method can be used in the metal hydride for understanding the cold fusion process. It is very interesting.